It's the party in the heart when you draw my line chains. It's the breaking of the waves, the world probably really counts some brains. It's a major melody out there. It's a solitary sequel. You never know anything at all. It's the ticking of the clock when you wake up and know it's 7 a.m. It's the thought of getting used to something so right, just throw it away. It's a major melody detail on the morning train. And the fear of having to go back, you'll hear the piano sound and know something turn around. It's the circus every now whenever I reach out to touch you again. It's the laws of our attraction and the fact that it's all going somewhere. It's a major melody, like the waves of that woman's trail. So one day I can feel you, you hear the piano sound, and know someone turn around. It's the morning after everything's done and I'm about to begin. The starting on my left and that piano on the right is my day. It's a major melody, it's a solitary sequel to never knowing anything at all. To never knowing anything at all. To never knowing anything at all. To never knowing anything at all.
So just Nicholas, right? Wait, was there someone else who comes to class? Oh, Marco. Okay, let's wait another few minutes. And I mean, I know it is, well, firstly, after the typhoon, and secondly, also early in the morning. So let's wait a few more minutes. All right, everyone is here. Let's begin. All right, so today I'm going to start recording things. So I'm using a computer here. So I'll be sitting and doing the thing because I want the audio also to be captured. So then there'll be like a 2-hour video on YouTube afterwards of this, so you can revisit it. In parallel, also we have the reason for this class being at the time it is. So two of my students, Ihan and Eric, are also watching this online, I believe. So you have two more invisible partners. Okay. All right. So today we'll begin by finishing off the week 2 notes. So in particular, we'll mostly discuss Gilbert-Varshamov bound, Gilbert-Varshamov codes, and also we'll briefly discuss the algebraic geometry codes, just very, very briefly. Then we'll start week 3 notes. So can we have volunteers for week 3? So Nicholas, Marco, Amitalok, one of you. Okay, Amitalok for week 3. Okay. Okay. So, but for week 2, it's still going to be Chachi, right? So you'll finish taking week 2 notes. Okay. So a very quick recap of what we discussed last week. We talked about like the Hamming bound and then also the Plotkin bound. So the Plotkin bound told us that, let's see, there should be a curve somewhere over here. The Plotkin bound told us that for p less than a quarter, no positive rate is possible. And indeed, even for p less than a quarter, you can't hope for a rate greater than 1 minus 4p, right? So it told us that really the adversarial BSCP channel is indeed a different beast than the binary symmetric channel with crossover probability p. The capacity is indeed smaller. So far we've focused on converses. We'll do now one achievability, a very simple achievability, I think, but also quite the best one known so far, at least for small alphabets. And then we'll do two more converses, and that'll sort of well. So then we'll do two more converses: the Elias-Bassalygo bound and the Gilbert-Varshamov bound. Sorry, the Elias-Bassalygo bound and the LP bound. Those are Week-3 materials. Okay. So what are Gilbert-Varshamov codes? So when p is less than a quarter, these give constructions. These give constructions of codes that achieve positive rate when p is less than a quarter. And again, the constructions are quite straightforward. So we'll actually look at, there are at least 3 known constructions. I'll focus on 2 of them. We won't discuss the third one. Because, you know, like again, the hope is to generalize these constructions for binary or Curie symmetric channels to general ABCs. So over here, like it's good to know how to construct these codes in different ways. So one construction, the first construction is just this greedy construction, which is, as the name suggests, greedy. So you start off by choosing any sequence, any n-length sequence. So let's say you choose a vector x1 and put it in your code book. And now you have to throw away the sequences in the Hamming ball centered at x1 of radius 2 and p, right? Because remember, in this adversarial channel, in the adversarial BSCP channel, the adversary can flip up to pn bits. So if you choose some x2, which is within the Hamming ball, then the adversary would be able to confuse x1 and x2 by pushing to something in the middle, right? By getting the same y in the middle. So you really have to throw away everything in this Hamming ball over here, and then you choose an x2, and then so in the complement of this, then throw away everything in the Hamming ball centered at x2 of radius 2 and p again, and then in general at stage I, choose something outside the union of the balls that you've chosen so far, right? Because if you're in the anywhere in the union, then you're kind of screwed. So clearly the Hamming distance between any pair of codes is at least 2pn. That's guaranteed. And here's the very crude calculation that's usually done. And surprisingly, like up to polynomial factors, this is really the best that's known. So at each stage, you're throwing away at most the volume of a Hamming ball, at most the volume of a Hamming ball of radius 2 and p, right? But the volume of a Hamming ball of radius 2 and p is 2 to the n times h2p, is not equal to that, right? So therefore, the number of times you can do this is at least 2 to the n divided by 2 to the n h2p, which is 2 to the n 1 minus h2p, right? Now, what this clearly ignores is the fact that in general, you know, once you start choosing multiple Hamming balls, there'll be more and more intersections between these Hamming balls, right? So this quantity over here, like 2 to the n h2p times 2 to the nr, is clearly heavily overcounting the number of sequences, right? Because sequences in this region, for example, are in 2 different balls. Sequences may be over here or in 3 different balls, and so on. So this is generally speaking heavily overcounting, but all the more careful analysis that people have tried doing only increases the rate by a sublinear, by a subconstant term. So basically, instead of getting 2 to the n times 1 minus h2p, they get some polynomial times 2 to the n h2p. So the rate doesn't really improve, at least via more careful approximations. There's still approximations. There's still not a good understanding of like if you did this in a more careful manner, like if your greedy construction carefully chose, so once you've chosen x1, how do you choose x2? Like maybe you put it x2 right outside the boundary of x1. Then maybe you choose x3 in in a structured manner, like maybe in a lattice or something like that. So firstly, it's not clear how to choose these objects in high dimensions in that greedy manner, and secondly, it's not clear how to analyze the wastage in this analysis. So the really, like for small alphabets, the best known construction that are just give you rate 1 minus h2p. Okay, and note, by the way, 1 minus h2p is positive when p is less than a quarter, because 2p is less than a half if p is less than a quarter. So therefore, h2p is less than 1, because the entropy function equals 1 only when p is when the value is a half, right? So for p less than a quarter, this quantity is positive, so it does indeed get a positive rate when p is less than a quarter. Now, for the same for this, to get the same rate, there's a different construction that's known. This is a linear code. Notice in this construction, in the previous construction, the greedy construction, the design complexity, the encoding complexity, and the decoding complexity in principle are all exponential in it, right? The design complexity, well, you have to design an exponential number of code words, so that's exponential in n. The encoding complexity, well, you either you have to store an exponential number of code words, using storage and encoding complexity interchangeably, because either you have to store an exponential number of code words. Well, you do have to store an exponential number of code words. So in that case, the storage complexity for encoding is exponential, and for decoding also, like besides the fact that you have to store the code book, you also then have to search for the nearest code word. And at least the brute force decoding complexity, you would have to check all of 2 to the n possible sequences. So therefore, the decoding complexity is also exponential, right? Which isn't to say that there may not be cleverer ways of doing this, but at least the naive way of doing it via greedy construction is just bad. There is, well, at least from complexity reasons, a somewhat better construction, linear codes. These linear codes have lower encoding and design complexity. The decoding complexity is still bad; it's still exponential. Okay. So the idea is you choose a random generator matrix G over F2, and what did I write here? I don't know what this n less than whatever is, but basically the rate that you choose is just slightly less than 1 minus h2p minus epsilon. Okay, so the rate is essentially the same as the greedy construction, just epsilon less than that. And then your generator matrix dimensions. These are the dimensions of the generator matrix. So it's got n rows and nr columns. Okay, so therefore the code is then the collection of all x vectors, all n-length binary vectors that result from multiplying this generator matrix with your message vector. Your message vector is a binary vector of length n times r bits. Okay, so view the message vector as a column vector with nr bits. View the generator matrix as this n by nr matrix, and then you get the collection of code bits. Now, so you choose this generator matrix uniformly at random. Now, the code is just this collection. The minimum distance is greater than 2pn if and only if the minimum weight code word is at least 2pn, right? And the reason for this is because for linear codes, the minimum distance between code words is also the minimum weight of any code word in that code book. And the reason is because the code is linear, therefore the difference between any pair of code words must also be a code word. So in particular, the vector corresponding to the two closest code words, that x minus x prime, must also be a code word. And therefore, you may as well just look at the minimum weight code word, right? This is a standard fact about linear codes. Okay. So really, we are therefore trying to compute the probability that for a random generator matrix, there is a code word of weight 2np within the of weight 2np. So that's basically in the Hamming ball centered at 0 of radius 2np. There is a code word within there, right? So think of it in the following way. First of all, fix your m, and over the randomness in G, ask yourself what is the probability that the code word x as a function of m, and G, is within that Hamming ball. Okay. So what's happening over here? You fix this message vector m over here. This G is random. So for a random G over here, what is the probability that the resulting x over here is of Hamming weight at most 2np? So the way that would happen is, well, so first of all, the first bit is 0 or 1 with probability half, because the first row of this matrix is 0 or 1 with probability half, right? So this is 0 or 1 with probability half. This is 0 or 1 in an independent manner with probability half, and so on, right? So because of this, the probability that you end up with something of Hamming weight at most 2np is n choose I, where I goes from 0 to 2np. So it's summation this divided by 2 to the n, right? Because what you want is that at most I locations are 1s, and this is just doing that combinatorial calculation. It's just summing up the probabilities I going from 0 to 2np of there being I 1s. And this quantity is 2 to the n h2p minus 1, right? It's not equal to that, ignoring the polynomial factors. Okay, so this was for a fixed m. So now the probability that there exists any code word within that Hamming ball, well, you have to take a union bound over all the possible messages, right? The number of possible messages is 2 to the nr. So if you choose your r to be less than 1 minus h2p by epsilon, then this probability is less than 2 to the minus n epsilon, right? So what this is saying is that for most G matrices, like a large fraction, 1 minus 2 to the minus n epsilon of them, the minimum distance is at least 2n. By the way, over here, we did the calculation for a uniformly random generator matrix. Instead of a uniformly, this is not within the notes, but maybe the note taker can also take note of this. So even if you do not do it uniformly random over all possible matrices, even if you do it with, let's see, yeah, okay. So even if you do it with a different ensemble, so for example, so there's a paper called On the Distribution of Rank of a Random Matrix Over a Finite Field. So using results from here, you can argue that even if the matrix chosen is not Bernoulli half, each entry is not Bernoulli half, but each entry is, let's say, Bernoulli Q, where Q can be very small or very large. It can be as small as log n over n, or as large as n minus log n over n, right? So anywhere in that range, even if you choose things IID, then you can basically make things still work out. Like the probability of a code word bit being a 0 or a 1 is still a half, right? And then you can still make things work out. So why is that interesting? Well, so for example, if the matrix is very sparse, if it has like roughly log n ones per row, right, or log n ones per column, so firstly the encoding complexity is even lower, and secondly that starts getting to the point where you could imagine, so that's sort of in the regime where the sparse graph ensembles, like this starts intersecting with graphical methods in encoding and decoding. There's a difference here, because here you'd be sampling the generator matrix uniformly at random from a sparse ensemble. Usually for sparse graph methods, it's the parity check matrix, that the low density parity check matrix, right? but there's still some overlap between these notions over here. Okay? So anyway, very quickly, just to emphasize, you don't have to choose Bernoulli half matrices. You could choose Bernoulli Q, where Q would be really quite close to 0 or 1, and you can still replicate the same type of result. Okay. All right. Moving on. So we talked about these two constructions. Let's and prove them. There's a third construction, which is useful in some scenarios. In fact, maybe there's even a fourth. But right now, let me just very briefly mention a third, and we'll see it again in a few weeks when we revisit adversarial channels. So this third construction is you just take a random code, not a random linear code, not a greedy code. We just take a random code with 2 to the n code words, and then throw away a few of the bad code words. So throw away the code words which are less than Hamming distance 2pn from their nearest code word. Okay? So over here in this case, what you have to show is that you don't have to throw away too many code words, and even then you can end up with something which is at the right minimum distance. Okay? That's a slightly more detailed argument. It requires certain types of concentration inequalities which you haven't discussed yet, but so that's why I won't do it. But that's also a third potential way of doing it. And there are potentially other ways. What's surprising is each of these ways seems to end up giving us basically the same rate of rate 1 minus h2p. So it seems somewhat fundamental, right? This 1 minus h2p being kind of a fundamental rate, at least in terms of different ways of constructing things greedily, randomly, via linear codes. They all seem to end up at the same rate. So there's something going on over there, right? But that's just the way it is. Okay. So one more homework problem, and by the way, for Eric and Ihan, let me repeat. So this is week 3. So at the end of this week, we'll have our first round of homeworks. And the way we'll do the homeworks is, like throughout these notes, there's been a bunch of like suggested homework problems mentioned in these notes. So we'll assign different subsets of these homework problems to different people. Or at least we'll set up a grid, and then people can select maybe 2 of them, or 2 per person, and so on. So you can collaboratively try to solve these problems. Okay. So anyway, one potential homework problem here is, so replicate both the GV constructions above, so both the greedy construction and the linear code construction for adversarial QRE symmetric channel with symbol change fraction p. Okay, so this should be A QSEP, adversarial QSEP. Okay. So like we said for the Plotkin bound, there's a generalization for general AVCs. There's a generalization for general AVCs also for GV codes, and in fact other types of codes as well. So for cloud codes, these are also new. These are unpublished. So, but we'll discuss these in a few weeks when we revisit the zero error coding theory. We revisit adversarial like zero error channels. Okay, now in passing, the last thing I want to say about week 2 notes is algebraic geometry codes. So I'm just going to state it as a fact. It's a highly non-trivial fact. So these algebraic geometry codes are in some sense generalizations of Reed-Solomon codes that we'll discuss in week 3. What they do is they choose certain curves, certain equations like elliptic curves or things like that over finite fields, and then choose roots of these solutions as code words. Okay? So what can be shown is that when the finite field size is k square for some prime number k, then there exists a code over fq such that the rate of the code is 1 minus 2 times p minus 1 over square root of q minus 1. Okay. How does this come about? These are entirely non-trivial facts about elliptic curves over finite fields, and it can get very deep very quickly. In all honesty, I'm not very comfortable with these materials right now, but at least as a headline result, in the 90s, these were discovered, these sorts of codes were discovered. And when you do this calculation, then you just numerically calculate it. When q is bigger than 49, then 1 over square root of 7 minus 1. So this becomes 1 over 6. So you can get rates higher than 1 minus 2p minus 1 over 6. And for q equal to 49, if you plot the corresponding GV code, so remember the GV bound that we derived over here, over here is for the binary case, and you would have to do what this homework suggests, to do the corresponding query case. So when you look at the corresponding query GV code rate, that is indeed smaller and not equal to the corresponding algebraic geometry rate that you can get. So this algebraic geometry rate looks like a curve kind of like this, and the GV rate is maybe very badly drawn, but it's a curve kind of like this, which is smaller, at least for some values of p, for sufficiently large q. So not asymptotically large q, a concrete value of q, like 49, right? And then you can beat the corresponding GV rate. Okay. So I think that covers it. So we already discussed this material in the last class, the construction of bounds beyond the construction of codes beyond the zero threshold bound given by the Plotkin bound via linear programming. So I believe this finishes week 2 notes. Any questions or any comments from people in class or people on Google Hangout? Eric, Kihan? Okay, anyway, no response from them. I'm hoping they're still there, but whatever, it's not being recorded, right? By the way, okay, Eric is typing something, so they're there, they're awake. It's late night, they're evening, but whatever, no questions. By the way, the audio quality is okay, and the video quality? Okay, they're typing something, so we'll see if we can change something. Okay, so just let me know if you want me to do. Okay, so audio video is okay. Okay, good. So let's move on to so this is not what I wanted to talk about, to week 3 notes. So there are week 3 notes. Yeah, okay. Okay, so let's begin with the so-called Johnson bound. So, okay, so far we've seen 2 upper bounds and 1 or 2 lower bounds, well, several lower bounds for code construction. Now let's go back to upper bounds on the sizes of code. So this is the so-called Johnson bound. Let me make this larger. Let's see. Okay. So the Johnson bound is of interest by itself, but that will be later in the context of so-called list decoding. But for now, let's just view the Johnson bound as a preliminary, as an intermediate result for proving an interesting bound called the Elias-Bassalygo bound. That's the next one. So it's an intermediate stage. Indeed, it's basically the most of the calculations for the Elias-Bassalygo bound happen over here in the Johnson bound, and it tells us the following. It says, so suppose you have a binary code, and again you can replicate these calculations for query cases as well, and we can make that a homework problem. But for a binary code of length n, such that the minimum distance is d, which is delta n. So just parameterize d as delta n. So suppose someone gives us a code with good minimum distance properties, then it must be the case that any sufficiently small Hamming ball does not have too many code words within it. Okay. So more precisely over here, suppose you choose a Hamming ball BH of radius WN centered at any x. Okay, so it doesn't matter where you choose the center. Choose the radius to be WN, where W is larger than P, but not too large, like not like 1, not like half, right? So because a Hamming ball of radius half already has basically 2 to the n sequences within it, right? A Hamming ball of radius half has something like 2 to the n over square root of n sequences within it. So I should have said half less than W less than P. So consider some Hamming ball over here where there's some concrete value of W, which we'll specify later. So what we'll show is, as long as W is not larger than a certain amount, some specific function of P, then no such Hamming ball can intersect too many code words, more than a polynomial number of code words, from the code over here. Okay. So in particular, suppose, so let's look at C prime, which is the collection of code words C, which are X prime minus X, where X prime are code words. So this should be the code intersect with Hamming ball X and W. Okay. So I'm missing a C over here. So this X prime, this is a code word from the original code. X prime is a code word from this original code over here. It's also within the Hamming ball X of radius NW. So it's the C intersected with B, X, and W. And this new code, C prime, is just recentered around X. So really all that's happening is I look at X as the center of a Hamming ball. X may be a code word, may not be a code word of the original code. It's just some sequence. Okay. I look at a radius W and Hamming ball around it. And then I view the original code words, X prime, X double prime, and so on, as being within the Hamming ball around it. So I can just instead think of this as X prime minus X, X double prime minus X. So I can recenter this X as the zero vector, so to speak. And then these code words over here become, code words of weight at most NW within C prime. Right? Amitalok, you were looking a little puzzled. Is that okay? Yeah, so that's fine. All right. So okay. So now every code word in this C prime is a length n binary vector of Hamming weight at most Wn. Right. Okay. So really, this is like saying, suppose you have a ABC where the input alphabet, output alphabet, state alphabet are all binary. Y is equal to X plus S. And now you have a weight constraint on the input. So the input code words are constrained to be a weight no more than n times W. And you have noise constraint on the adversary. So the Hamming weight of the state vector of the noise vector is no larger than n delta by 2. Right? Then in that case, if W is sufficiently small, so what are we interested in now? We are interested in a Plotkin type bound for this regime, right? Because what does the Plotkin bound tell us? It tells us that if the problem is sufficiently constrained, so far what have we seen? We've seen in week 2 that if P is sufficiently large, if P is greater than a quarter, then you can't have more than a constant number of code words. The number of code words in your entire space is no more than a constant over there, order 1 over epsilon. Right? Here in this setting, we're doing the opposite. We're keeping the P fixed. So P is some quantity less than a quarter. Okay, P is some quantity less than a quarter. So we're keeping P fixed, but now we're reducing W. So instead of making the noise large, we're reducing Alice's power. We are making W small, okay? And we'll observe a similar behavior, which is once W becomes sufficiently large, then you can't have too many code words over here, okay? So that's just intuition about what the calculation we'll do. The calculation we'll do will look a lot like the Plotkin bound. We'll do it in one specific way, and one of your homework problems will be to rederive it in the other way that we know how to do it, okay? So in particular, we'll do this calculation separately for every W prime less than W. Okay, so what does that mean? So decompose your C prime as a union of code books, C prime, W prime, or W prime less than W. So just think of it as different shells of radius W prime centered around X, okay, and take a union over all possible W primes less than W. And we'll argue that in any of these shells, there can't be too many code words. So overall, there can't be more than Wn times the number of code words within any shell over there. Right? So that will be our proof strategy. So within each shell, each code word will be of Hamming weight exactly W prime. Right? And it's possible to do this calculation more directly without doing this decomposition into shells, but that just gets analytically a little bit messy. So right now, we'll just simplify our life a little bit and focus on Hamming weight exactly W prime. Okay, so remember the Plotkin bound, we derived it in two different ways. One was algebraic via so-called double counting method. We looked at the quantity, the pairwise Hamming distance between pairs of code words summed over a whole code book. That is an algebraic way, a double counting way, and that's how we'll prove the Johnson bound. There's also a geometric way of doing it, which I encourage you guys to think about. That will be one of the homework problems, John. Okay, so that geometric way is again very similar to the geometric way of proving the Plotkin bound, but under different choices. So, like before, the double counting way will examine the pairwise Hamming distances between code word C and C prime, both within this C prime, or this should be C prime W prime. So both of them are code words of the same Hamming weight W prime. Okay, so this is a typo. There should be C comma C prime within the cal C prime W prime. So they're both of Hamming weight W prime. And clearly, for the same reason as before, this is no more than twice of C prime choose 2, C prime W prime choose 2 times delta n, right? Because at most, because the pairwise distance is at least delta n for every pair of code words, and the number of pairs is twice of C prime W prime choose 2, right? So therefore, this is at least this quantity over here. Now, and again, just like the Plotkin bound, the double counting way over there, the Hamming distance between C and C prime, this is also a typo. This should be summation overall C comma C prime. So this should be summation overall C comma C prime within that C prime W prime. This quantity, just like the Plotkin bound before, is like if you look at the ones in any column, that's SI. Then the zeros in any column is therefore C prime W prime minus SI, right? So therefore the total contribution due to this particular coordinate to this summation overall C comma C prime DH C comma C prime. So that contribution is exactly 2 times SI times C minus SI, and then sum overall n. So it's exactly the same as before, right? So nothing different there. Now, so far it's just been the same as the Plotkin bound, but now we have to put in the weight constraints. So we have to use the fact that the code words within the C prime W prime are of Hamming weight exactly W prime. So how do we do that? So firstly, we note that 1 over so the summation of SI I goes from 1 to n is basically the sum of all the ones in the entire code book, right? It's the sums of the Hamming weights of all the code words. So this summation over here. Now each code word is of Hamming weight exactly W prime n. So therefore, if I divide by C prime, I should get W prime n, right? So this thing here is basically just a fact. Is just stating that the Hamming weight of exactly of each code word is exactly W prime n, and therefore the average Hamming weight is also W prime n. That's all that this is saying. So you just rearrange terms to get this thing here. Separately, by the Cauchy-Schwarz inequality, you get something like this, right? How do we get that? So the Cauchy-Schwarz inequality, remember, tells us that the dot product square between two vectors is no more than the square of vector L2 norm square of vector 1 times L2 norm of square of vector 2. So think of vector 1 being like the SIs. Okay, so the vector 1 is an n-length vector whose components are SI. Vector 2 is an n-length vector whose components are each of them identically equal to 1 over n. So therefore, their dot product is 1 over n summation SI, right? Because you can pull the 1 over n out, right? So therefore, by Cauchy-Schwarz, you get this square on the left-hand side is less than or equal to this square times this square. which is summation si square divided by n, because there are n terms here, so you have 1 over n square times n, that gives you 1 over n, right? Okay. So now what do we therefore know? We know that let's see, w prime square and yeah, okay. So wait, how did I write this? So w prime square c prime square. So that looks like a square of this quantity here. Okay. So this square is the square of 2, which is the square of 1 over n summation si whole square, which is exactly the left hand side of this inequality here, which is less than or equal to summation si square by this, right? So that's how we end up with this inequality 3 over here, right? Okay. So now what do we do? So we have so this quantity times delta n is less than or equal to 2 times summation si c minus si. That's just the same calculation as before, as in the plot bound. So this quantity is larger than or equal to this quantity, just like in the plot bound, right? So now when we open this out, the first term is linear in the SIs, and the second term has the SI square. So that's where this equation 3 will come in handy. Okay. So by the way, everywhere over here, this should have been a C prime W prime, right? So each of these are for the fixed weight code words, So over here, so now when we do this, so summation SI, just like before, this is basically just the sums of the Hamming weights of all the code words. So therefore, we end up with n W prime C prime, and this quantity we just use this inequality over here. And you get something like this, and then when you go to the next page, certain things cancel out. The n times the size of the code book cancels out, and you rearrange. And then my handwriting suddenly changed for some reason for a few lines. So then you end up with the size of the code is at most delta over delta minus 2w prime plus 2w prime square. So if the denominator over here is positive, if the denominator delta minus 2w prime plus 2w prime square is a positive quantity, then what does that tell us? It tells us that the size of the code is at most a constant, just like the plotkin bound, right? It tells us, or more precisely, it tells us that the number of code words within a shell of radius w prime is at most a constant, and therefore the overall number of code words is at most linear within that ball of radius w prime, right? So so the roots of this equation, the roots of this quadratic equation in w prime are like this, and you rearrange them, and you get half times 1 minus 1 plus minus square root of 1 minus 2 delta. Now we are interested in the regime where w prime is less than a half, because if w prime was greater than a half, then really, as we already argued, if w prime is greater than a half, then it's basically unconstrained, right? Because Alice can choose code words of Hamming weight half, and that's just the GV bound. Like when she can choose code words of Hamming weight half, then when you plug in the GV bound, like when you try to construct things that way, then you basically get the GV bound. So therefore, the w prime that we're interested in is the smaller of these two quantities. It's half times 1 minus square root of 1 minus 2 delta. And what that tells us is that if over all the w primes less than w, like if all the w primes are less than this quantity over here, then the number of code words within each of those shells is at most a constant. And therefore, bounding, like, just summing up, just taking a union bound over all possible w primes less than w, you end up with order n code words if w is this quantity. Okay, so all these calculations, but the bottom line is just this. It says that if you choose a Hamming ball of radius nw, if you choose any Hamming ball of radius nw, then if your original code, like unconstrained code, was good, had pairwise distance at most, at least 2 times np, then the number of code words within any Hamming ball of radius w can't be too many, at most linear. Okay, and this is in the literature. It's a so-called list decoding bound. We'll see list decoding more explicitly later, but just keep that in your mind for now. And we, to prove this, we did it via looking at the connection with constrained binary codes, constrained adversarial binary codes, and we derived it that way. Right? Okay. So as I mentioned, this Elias-Bassalygo bound is interesting the Johnson bound is interesting by itself, but for now it's interesting mostly because of the connection to the Elias-Bassalygo bound. Oh, I forgot to put this in here, but another homework problem to add to the list, and if the scribe for today, that's Amit Alok, can add that to the list. That is, so over here we did the proof via the double counting method. This proof can also be done via the geometric method, and that should be a homework problem as well, okay, to add to the list. And yeah, so since at the end of this week, we should be giving out homework problems to different people. So if the three different scribes so far, Jack, Chao Chi, and Amit Alok, can send me a list of what we have marked as homework problems so far, then I can construct a list and we can do that assignment later. Okay. All right, so it's like 50 minutes in. So let's just spend a few minutes talking about the Elias-Bassalygo bound and putting them in context. And then we'll take a 5-minute break, and then we'll do the last topic for today, the LP bound, okay? Which admittedly will be a little bit intense, but that's like. Okay, so given the Johnson bound, what is the Elias-Bassalygo bound? The Elias-Bassalygo bound says, okay, now the same thing as before. Suppose someone gives you a code with minimum distance delta n, the size of the code is 2 to the nr, then there is at least one Hamming ball of radius nw. So there is at least some center x where you can put a Hamming ball of radius nw, where there is at least the average number of code words within that Hamming ball. So what is this quantity over here? It's basically 2 to the, okay, so on average, a Hamming ball of radius nw has a fraction, occupies a fractional volume 2 to the nhw divided by 2 to the n of the total space, right? So therefore, if, like, just as a thought experiment, suppose the code was a random code, then the expected number of code words within that Hamming ball, you would expect to be 2 to the nr times this fractional volume, right? Now, it's not necessarily a random code, it's any code, but at least one of the Hamming balls must have at least this average number of code words within it, right? Because if not, you could just do a pigeonhole principle, look at all of the possible centers, add them up, divide by 2 to the n, and so on, and you'd end up with a contradiction. You'd end up with the fact that there are fewer than 2 to the n, 2 to the nr code words within the within the space over here. So therefore, at least one of them, one of the Hamming balls, has to have this average number of code words within it, right? So then combined, okay, so note that if r plus hw is greater than 1, because the exponents over here, when you pull everything to the exponent, you end up with 2 to the n times r plus hw minus 1. So if r plus hw is greater than 1, then the exponent is positive, right? It's larger than n. In fact, it's going to be exponentially large, right? Because again, if r plus hw is larger than 1, then the exponents in the numerator are larger than the exponent in the denominator. So that would be a contradiction, because the Johnson bound guarantees that no Hamming ball has more than order n code words within it, right? For a good code, no Hamming ball of radius w has more than n code words, as long as w is no larger than this quantity. Right? So you basically just do that. You plug in the fact that w is this quantity over here. W is half times 1 minus blah, and use this inequality r plus hw is bigger than 1, and therefore you know that r is the opposite of this inequality, r plus hw is less than 1, because you do not want this inequality to be true, right? So r plus hw is less than 1. So therefore you end up with r is less than 1 minus this entropy function, right? Okay, actually, let's do one more just quick calculation, and then I promise I will let you guys take a break. Okay. So far we've looked at So if you plot it out, the Elias-Bassalygo bound is everywhere below the punctured Plotkin bound. The punctured Plotkin bound is 1 minus 4p, and when you numerically plot this out, you can show that this quantity is always smaller than the punctured. Okay, it is above the GV bond. The GV bond is 1 minus H2p. The Elias-Bassalygo bond is above that, and there's therefore still a gap. Now, one last calculation before the break. So this calculation asks, okay, so clearly there's still a gap, at least visually, numerically, there's a gap between the Elias-Bassalygo bond and the GV bond. But at least in some regimes, how do they compare? Like, for example, when P is very close to a quarter, when P is 1/4 minus epsilon, let's say, then how do these two bonds compare? And for that, let's just use this useful fact, which is the derivative of the entropy function with respect to x is, it's like ln 2 times ln of 1 minus x over x, right? Just basic calculus. So if we do that, then suppose P is 1/4 minus epsilon, the rate of the GV bound at P is 1 minus H2P, which is 1 minus H half minus 2 epsilon, right? And the Taylor series of 1 minus H of x around a half is, when you use this, so you use the derivative of x, and you do these calculations, and just basically look at first order terms, like the first non-zero terms in epsilon, and you'll end up with 2 epsilon ln 2 ln 1 plus 4 epsilon over whatever. So basically this is also a pretty small quantity, right? Because you have ln of 1 plus 4 epsilon over a half, roughly. So therefore, you should expand this out by a Taylor series as well, and you'll end up with basically something that looks like order epsilon squared. So the GV bound gives us that when you're very close to the zero rate threshold, then our best known construction is order epsilon squared in terms of. How about the Plotkin bound? The Plotkin bound as an upper bound is clearly theta epsilon, right? Because the Plotkin bound is just 1 minus 4p. The punctured Plotkin bound is 1 minus 4p. So when P is 1/4 minus epsilon, when P is 1/4 minus epsilon, then 1 minus 4p just behaves like order epsilon, right? And for small epsilon is much larger than epsilon squared, right? So the Plotkin bound is much weaker than the GV bound. I mean, there's a large gap in terms of the ratio. There's a large gap between the GV bound and the Plotkin bound. And the Elias-Bassalygo bound is not much better, because when you do the same thing over here, when you take the Taylor series over here, expand it out. So 1 minus 4p behaves like epsilon, and then use the Taylor series expansion here. Again, you get order epsilon or theta epsilon, right? So really, the ratio between the best upper and lower bounds over here is still a large gap when P goes to a quarter. So the LP bound helps resolve this, at least almost resolve this. So the LP bound tells us that no code can have a rate larger than epsilon squared log 1 over epsilon. So not quite epsilon squared log 1 over epsilon. But more than that, it also tells us that the best rate is, there's some expression for it, something like entropy of half minus square root of delta times 1 minus delta. And you can check via the Taylor series expansion that this means like epsilon squared log 1 over epsilon. In this case, you have to take the Taylor series around of the entropy function around 0, not around a half. Okay? But again, by a Taylor series, you can get epsilon squared log 1 over epsilon. Okay? This is the so-called first LP bond. There's a second LP bond as well, which we'll just mention briefly at the end of this set of notes, but we won't go into it. Okay. Now the LP bonds are going to be quite. It's going to be a long discussion, so I really should give you a break before then. It's also going to be quite technical, new tools which you learn along the way. I think that'll be quite interesting. But let's take a 5-minute break. All right. Break.
fields in the Czech Republic come alive with harvesters.
All right, time to return to class. So during the break, our overseas participants have not been inactive. Yihan has been asking a bunch of questions. Let me actually share the questions. Let's see, or a comment or something. Let's see, where did they go? So, okay, so his first point was the following. Let's see, can I? Okay, so yeah, so his first point was, well, instead of decomposing into different shells, we can directly argue that given a code, I mean, it's just an equivalent way of proving things. So instead of looking at each separate code, like each separate shell and bounding the number of code words in that separately, you can just say that there must be a shell with the largest number of code words, right? Among all possible shells, among all possible NW prime radius shells, just choose the shell with the largest number of code words. And now you have a constant composition code, right? And if you can bound the number of code words within this shell, then you automatically have a bound over all, like you have n times or NW times that many code words over all shells. So it's just a different way of thinking about it. It just says that you have a bound on the number of code words over all shells. Right? A potentially interesting question is, so why did we do this decomposition? Because it told us that each code word was Hamming weight exactly n times W, and in the double counting argument, then that just made the calculations easier. But perhaps by more carefully doing that analysis, by saying, well, different code words can have different weights, but no code word can have weight more than W, maybe one can do a tighter argument. What could one hope to tighten? So one could, instead of saying that having order n code words within the Hamming ball of radius NW, Maybe if you do it simultaneously over all shells, you can get order 1 or a smaller number of code words in the whole handle, right? So it's a second order issue. It's not really truly important, but it's just a thought. Like, can you tighten the analysis instead of doing the analysis shell wise separately? Can you do the analysis over all shells simultaneously and thereby reduce the number of code words within the form? So that's a question that's worth thinking about. And there's another issue about list decoding and so on. That's perhaps not directly relevant to today's discussion, so I'll leave that aside. Okay. So this proof, yeah, I mean, it's it's not trivial. It's going to take some effort and so on. And in all honesty, I've revisited this LP bound several times. There's a couple of different proofs. The first proof by McAleese, Ramsey, Rodmich, and Welch in the 1970s. It's a very hard paper to read, and the couple of times I've tried reading it or seen talks by it, it's hard. I mean, it just takes effort to understand. This proof, even though it's considerably simpler, is still non-trivial, right? So hopefully in the next half an hour or 45 minutes, we'll make some progress towards understanding it, but even then, it'll be worth revisiting. But besides the fact that the LP bound gives us the tightest known bound in the high noise regime, and then with some further ideas, the tightest known bound generally on the size of a binary code. Equally important, besides the consequences, is the proof technique. So this particular proof technique is a new proof technique using Fourier analysis on the Boolean hypercube. And getting familiar with this is potentially at least as useful as just learning the bound. Okay. So let's begin with some definitions, and then we'll highlight our proof strategy and then do some calculations, which end up getting a bit messy. So first of all, we'll say two sequences, x and x prime, on the Boolean hypercube, on the Hamming hypercube, are said to be adjacent if the Hamming distance is exactly 1. Okay, not 0, not 2, whatever, exactly 1. And then we'll denote it x as tilde x prime. So now let A be the adjacency matrix of the graph G, whose vertices are all binary sequences, and whose edges are given by x comma x prime, which are edges. Okay. So just as an example, so suppose you have the two-dimensional Boolean hypercube, the two-dimensional Hamming hypercube. Then in this case, these are your 4 vertices, and the adjacency matrix you can check. Like if you label the vertices 1, 2, 3, 4, then you have 1s over here only in the locations where corresponding things are adjacent. Yeah. Okay. Okay. So now, by the way, this notation here is slightly different from what's in the notes. So I've relied heavily on 2 sets of notes. So one is the original paper by Navon and Samorodnitsky, I believe that's how you say it. I may be wrong, but that's in this link over here. The other is a sequence of notes by Amnon Tashma and someone else, Dean something or the other. That's the link over here. I've tried to synthesize these to get sort of a hopefully simpler proof than is available in either of those places. Though there is considerably more material in both these sources that is also interesting, that is relevant, and so on. But just in the interest of brevity, I tried to focus on exactly the things needed for the LP bound plus a little bit of intuition. Whereas there's even more intuition, there's many more interesting things in those sources. Okay, so I would encourage you to look at them. Be a little bit careful of both of those. Like in both of those, I also found some errors, or at least what I think look like errors. Like in some cases, clearly typos, but in other cases, well, just messy calculations. Like I think things can be a little bit confusing. So while I heavily relied on these 2 notes, there's also some level of synthesis that went into these notes. Okay. All right. So in particular, one of those differences is this quantity over here. So this definition 3 says, for any set B, any subset of the Boolean hypercube, define lambda B as it's something like an eigenvalue, but not quite. It says, find the largest lambda such that there is some f supported in B such that AF is larger than lambda f. Okay, what is this saying? It's basically saying, so suppose AF was equal to lambda f. Okay, so first of all, A here is a matrix, F is a vector supported in 0, 1 to the F is a vector. Oh, I should not get up. I should be talking here. Okay, so F is a vector supported in 0, 1 to the n. So AF bigger than lambda F just means that the vector over here is component-wise bigger than the vector over here. Okay. So if this was an equality, then this would, and if this condition was not there, if F having like must have support within B was not there, then this is just the largest eigenvalue question over here, right? Now, suppose I restrict my F to be to have support within a particular set, like the non-zero values of F must be within a particular set. Then in general, there may not be any eigenvectors within that set at all, right? Maybe all the eigenvectors must have at least part of their support outside B. Maybe that's the case. So then I cannot demand AF is equal to lambda F, but maybe I can still demand that if my lambda is sufficiently small, that AF is component-wise bigger than lambda F, that equation may still be valid, right? So this is kind of like an eigenvector question over here, but with a limitation on the support of the eigenvector, so to speak. Okay. So this quantity lambda b will be fairly fundamental in the proof that follows. And it's related to a whole bunch of apparently very deep Fourier analytic questions, but for now, this is the definition. And in the notes, and in the paper, instead of this definition, it was F transpose AF divided by FF transpose. So, which is a slightly weaker condition than this one here, but I think the proof requires a stronger condition, not the weaker condition. Okay? So I may be wrong, but at least within the paper, it had a weaker definition. Okay. All right. So one note over here. So generally speaking, you've noticed that for vectors, I put the underbar over here, right? And it is true that F is a vector. It's a binary vector of length n. It's a vector supported on 0, 1 to the n. It need not be binary. F need not be binary itself. So in general, it's a vector. But instead of thinking of it like a vector, it will help to think of it like a function. Okay. So what do I mean by that? So over here, we're restricting F to have support within B over here, right? So this is like saying that, like, suppose B was just unit vector, the collection of unit vectors. So that's like saying that F is a function that maps the first unit vector to a real number. It maps the second unit vector to a potentially different real number, and so on. And it maps all the other non-unit vectors to the zero over there, right? So really, one way of thinking about this F over here, like when you look at all the vectors which have support for a specific B with for a specific binary vector within the set over there, then the corresponding F over there would have a corresponding largest lambda, and think of that as being the largest value. So it helps to think of this F. You have a question?
What do you mean by support F is B? So can you give an example?
Sure. So let's do an example. I'm going to do this on the board, so it may not be visible to the other people, but I'll try to speak it out loud. So it's just like saying, like, for example, suppose n is 3. So then you have all length 3 vectors. So the 0, 1 to the 3 is length 3 vectors. But now B, let's say, is the set of all vectors, is the set of all B, small b vectors, such that the Hamming weight of B is let's say exactly 2. Okay, and there are two such vectors, right? So given that, now my f's can be only something like I don't know. They must have. So there must be length 3 vectors, but at least one of these 3 vectors must have 0 in it somewhere, right? Because the support of a vector. So if I have f1, f2, f3, if all these 3 are non-zero, then the support is the vector corresponding to 1 in all of those locations. But if my vector is f1, f2, 0, for example, if my vector f is f1, f2, 0, then the support is in the first 2 locations, and it's 0 outside, right? So then the support of this vector f is within the set B over. Does that help answer the question? So Ihan thinks, he says it might be cleaner to think of x as length n binary vectors and f as real valued length. Yeah, let me just pull the comment up. So yeah, it might be cleaner to think of x as length n binary vector or b's, what I call b's over here as length n binary vectors, and f as real valued length 2 to the n vectors. So in Ihan's way of thinking, it's like saying for every b within this capital B over here, right? There are many vectors which have exactly B as that support, right? So there are infinitely many f's that have support exactly in the first 2 locations, but there is one which has the largest support, which corresponds to the largest lambda potentially, right? So think of it then as, so this comment is basically saying, think of f for for every 2 to the n possible. So what did I want to? So what is this saying? Yeah. So for every potential support. So in this case, so for example, n is 3. So there are 2 to the 3 possible vectors over here, right? For every possible support that you can have over here, there's a corresponding vector that I want to choose. There's a corresponding value that I want to choose for the lambdas, right? If the support was the all zeros vector, then there's a corresponding lambda I want to choose. If the support is the all ones vector, there's a corresponding lambda I want to choose, and so on. So this f over here is therefore assigning a lambda to every possible support vector. Okay. So this comment over here is saying that it may help to think of f as a function from 0, 1 to the one way of thinking about it is it's a function from 0, 1 to the n to r. Or if you look at the collection of all possible f's, then it's a function. Then these are real valued length 2 to the n vectors. Okay. Now this will become a little bit clearer once we start the Fourier analysis. So all I'm pointing is that this f has multiple different interpretations depending on the context. Okay. So once we start doing the Fourier analysis, then it really will be more useful to think of them as functions. Okay.
So what's the definition of support?
Oh, that's what I should have maybe said earlier up front. So the support of a vector f denoted SUPP of f is just the set of locations, set of coordinates, where such that fi, set of coordinates I, such that fi not equal to 0. Okay. So it's the locations where the vector is non-zero. So it's a set of locations where the vector is non-zero. So if you have the vector 1, 2, 0, 0, then the support is the set corresponding to the first 2 locations. Yeah. Any other questions? Okay, so hopefully these different ways of thinking about f will become a little bit clearer once we get into the things. Okay, so here's a related homework problem just to get comfortable with this. So firstly, there's sort of a straightforward observation that if you have two subsets B, B and B prime, and B is contained within B prime, okay, then lambda B is less than lambda B prime. And this should be really just clear, right? Because if B prime is larger than B, B prime contains more binary vectors than B, then you have less constraints on how you choose your F, and therefore your lambda prime for B prime will be larger than the lambda for B, right? So this first point should be clear, right? Okay, so now what's the largest that the set B can be? Well, the largest that the set B could be is 0, 1 to the n, right? It's all possible binary vectors because really B is a subset of 0, 1 to the n. So in particular, the largest that B could be is all possible binary vectors. So in this case, prove that this largest sort of eigenvalue, it's not really an eigenvalue, but let's just call it an eigenvalue for now. Prove that in this case actually it is an eigenvalue. So prove that this eigenvalue is n. Okay. And the reason that it's n, I've even given a hint here. So show that the maximal eigenvalue of an adjacency matrix is the maximal degree, and then bound the degree of the corresponding graph. And separately, find an eigenvector with eigenvalue n. Okay. So then you'd have an upper and lower bound, and they should match, and they should give you exactly. So that's a homework problem. So this tells us that this lambda B can never be larger than n, right? Because of this first property over here. And indeed, our goal, our proof strategy will be to lower bound the lambda for smaller b's. So the b's that we'll be interested in will be Hamming balls, and the Hamming balls will show, the first lemma will be to show that for any Hamming ball of radius r, the lambda br, this is a slightly different notation than the usual thing, because usually when we write Hamming balls, we write b and then the center of the Hamming ball and the radius. Now here I'm saying for any Hamming ball, so I'm neglecting the radius. This br is any Hamming ball of radius r. So this is trying to show that lambda of any Hamming ball of radius r is at least 2 times square root of r times n minus r minus some little o of n. Okay. So let's just digest this a little bit. This is saying that, so earlier we said that if you had an unrestricted eigenvector, if you truly had an eigenvector, then the largest eigenvector is n. Now, if you restrict yourself to choosing vectors whose support is at most, is at most r, okay, and you demand an equation like Ax is bigger than lambda x, component-wise, then what is the largest lambda that you can choose? Okay, and this thing here is saying that if the set of supports you're allowing are Hamming balls of radius r, then that lambda behaves like this quantity over here, 2 times square root of r times n minus r. Okay, and this is a purely algebraic proof. It won't require Fourier analysis. We'll do this first. Secondly, and this is where Fourier analysis will come in, this thing, the second lemma will show that if you have any code, any binary code with minimum distance d, let b be a binary vector such that lambda b is larger than n minus 2d plus 1, then the size of the code is at most n times the volume of b. Okay. This is a very mysterious lemma over here. We'll see. Okay, so this lemma is true for any code at all, and it's true for any set at all, as long as the lambda b for that set is sufficiently large. Then it's saying that the size of the full code can be bounded from above by n times the size of the potential supports of b. Okay, that's what this thing is saying. Now, specifically in the context of linear codes, suppose C was linear, then there's an interpretation to this thing. We'll see that below. Okay, so that gives some idea about how someone may have, first of all, thought of a lemma like this, and some physical intuition, some geometric intuition. So we'll see that later. Okay? So that's one observation. But the other observation is that these two lemmas together will basically allow us to prove the LP bound. Why is that? Because, so for example, suppose you choose R to be n by 2 minus d times n minus d. How did I choose this? Well, basically by equating these two quantities here, you get a quadratic equation. You solve that quadratic equation, and then that's what you get when you for your R over here. Okay, because look, R occurs as a quadratic over here, right? R times n minus R. So really, if you just solve that quadratic equation, you get this. This is one of the roots. So if you set R to be equal to this quantity, then 2 times square root of R times n minus R is just this quantity here. You can expand it out. You get 2 times n by 2 minus d, which is n minus 2d. So therefore, if you choose R to be just slightly yeah, I mean, if you choose R to be basically this quantity, yeah, so just slightly larger than this quantity, like plus little o of n, then you get not just n minus 2d, but n minus 2d plus 1, right? Because if you increase your R a little bit, then this quadratic over here, d times n minus, like this R over here, so sorry, this R times n minus R is an increasing function in R. So if you choose your R just a little bit larger, then instead of n minus 2d, you'll get that n minus 2d plus 1. And since n minus 2d plus 1 is larger than 1, so the size of the code is no larger than n times b, right? And n times b will be n times h of half minus square root of delta times 1 minus delta. How did I get this quantity here? This R divided by n is just half minus delta times 1 minus delta, right? Like if I normalize with n over here, then R over n is basically half minus square root of delta times 1 minus delta. So what this is telling us is that in that case, C is less than n times b is basically just saying it's 2 to the n times this quantity here, and that's the first LP bound. Okay? So if we can prove these two lemmas, then we're done. That's the LP bound. Right? Any questions before I proceed? Okay. So yeah, one more thing before we actually jump into the proof. So while this thing here is indeed what we need for proving the LP bound for any code, linear or non-linear, suppose C was linear, then there's a very nice interpretation. It basically says, okay, so suppose C is linear and C perp is the dual to C. Okay, so what is C perp? So for linear codes, the dual code is a collection of all vectors such that the dot product between x and oh, this is a typo. This should be x and x prime is equal to 0 for all x prime within the code. This is a typo. So basically, it's just saying, like, look at, so the original linear code had a bunch of x primes, okay, and now your dual code are the collection of all vectors which are somehow orthogonal to the original linear code. So a linear code, if you think of them as forming a subspace of binary or query vectors, the dual to that linear code are the vectors in the orthogonal subspace to that original linear code. Okay, and take orthogonality with a pinch of salt because like dot products don't really make sense over finite fields, but you can still ask, like, is the inner product of a vector z with another vector 0? So in that sense, you can still define orthogonality, and therefore you can still define the dual of a code, right? So that's what the dual of a code is like. So note also that the size of C and the size of C perp, when you multiply them together, this is 2 to the n. Why is this? That's precisely because the set of vectors which are perpendicular to every vector in the original code are in the null space of that code. So therefore, the rank nullity theorem tells us that the size of C plus the size of C perp, like the dimension of C plus the dimension of C perp is n, right? And therefore, the number of code words, like this product over here, is 2 to the n for binary codes, q to the n for query codes, right? Okay, so therefore lemma 1 implies that Hamming balls of radius r around the code words centered over the code words of the dual code is bigger than 2 to the n over n. Why is that? So, oh, this should be lemma. Sorry, this should be lemma 2. So, yeah. So lemma. This is not lemma 1. This should be lemma 2. So lemma 2 is basically saying the size of the code is yeah. So the size of the code is no larger than n times b. Yeah, and the size of the code is exactly 2 to the n divided by the size of the dual code. So that's less than nb. So just imagine taking Hamming balls of radius b, center them around each of the code words in the dual code, and that quantity must be at least 2 to the n over n. Like just rearrange the c is less than nb and view Hamming balls of radius r around the dual code words. So that tells us that the code words of the dual code essentially cover. So this r is called the essential covering radius of the dual code. It's saying that if I take Hamming balls of radius r in the same space in 0, 1 to the n, and put them at the centers of the dual code words, then you'll cover most of the volume of the Hamming space, at least 1 over n fraction, which is a polynomially small fraction of all possible binary vectors, right? So that's why this is called the essentially covering or the essential covering radius. So this way of thinking about things, at least for linear codes, gives a relationship between the minimum distance of the original code and the essential covering radius of the dual code. Okay. So even though for non-linear codes you cannot define a dual code because like the original code is not necessarily linear, so there may not be any dual, like there may not be any single code word, any x prime which is perpendicular to every x in the original code, that may not exist, and so on. So dual codes may not exist, but the essential covering radius still exists, the dual distance still exists, and so on. So via that connection in Fourier analysis is how these things go in. Okay. Now, at least for the purposes of our proof, this thing is not truly important. For the purposes of our proof, just lemmas 1 and 2 suffice. Okay. So okay, we're it's like 11.7, so we won't be able to do both the lemmas. But let's skip the Fourier analysis proof. Let's go directly to the calculations to prove lemma 1. It's a little bit easier than lemma 2. So let's do lemma 1, and then in the next class, we'll pick up with lemma 2. Yes? So in which example? Yeah. So over here, I mean, well, look at lemma 2. So lemma 2 says that that if you have a minimum distance d such that the lambda is bigger than n minus 2d. So the connection is this indirect connection through the corresponding lambdas. So lambda is bigger than n minus 2d, and lambda also has to be bigger than 2 times square root of r times n minus r. So through this, you can get a connection between r. This r is really the covering radius for the dual code, and the d is the minimum distance of the original code. So that's the interpretation. Any other questions? Okay, so let's jump straight into lemma 1. That I think is in the Von Pavlovsky paper. I think that's something like proposition 1.3 or 1.4 or something. You can find it. Okay, so we'll skip all this Fourier analysis. We'll return to it later. Now let's go to the proof of lemma 1. And for this, I've used these notes over here primarily, again with just cleaning up a few typos. Okay. So So recall, the goal is to show that there's a eigenfunction or eigenvector roughly whose support is the Hamming ball. And we'll begin by proving a weaker goal, which is that the dot product between AF and F divided by dot product between F and F is at least lambda, which is 2 times square root of r times n minus r minus little of. Okay, this is a weaker goal because this being larger than lambda would be implied by AF is bigger than lambda F, right? If AF is bigger than lambda F, then just taking the dot product with F on both sides and then pulling the FF transpose down over here would give us this implication. But it's not obvious that if this is true, then AF is bigger than lambda F, right? Did people understand what I just said? Okay, so we'll first prove this weaker goal, then we'll amplify it to the stronger goal that we want, which is AF is bigger than lambda F. Okay. Okay, so to prove this, we instead show, something more. We'll find a F which is, so instead of finding a F such that AF is bigger than lambda F, we'll do that. But we'll also find F is non-zero everywhere, which is more than we want, right? F will be symmetric. What does that mean? It means that for any x of the same Hamming weight, the value of the function will be identical. Okay, f of x will be identical for any x of the same Hamming weight. So in some sense, we can just use fi, I being the Hamming weight of x, to denote the value of the function, right? So just n numbers will suffice to specify the function, rather than thinking about like specifying the function for all 2 to the n possible values. Okay, so so in particular, think of so let's just choose capital M to be square root of n, which is of course little of n, and define the function f such that for all binary vectors of Hamming weight I is within the range r minus m, which is r minus square root of n till r. Define it to be 1 over square root of n choose I and 0 otherwise. Okay, so again, remember, what do we have to find? We have to find the f such that AF is bigger than lambda F. A is the adjacency matrix, right, for the binary hypercube. And we want to find AF is bigger than lambda F, lambda being this value over here, for every F supported within that. And in this case, we did do that, right? Because this F is 0 if I is bigger than R, or in fact less than R minus M, but that's okay, right? So F is 0 if the Hamming weight of X is bigger than R, so it's supported within that, so that's fine. And now we'll do some calculations, and we'll show that that this AF comma F divided by F transpose, like F inner product with itself, is bigger than lambda. Okay. So far, so good. I mean, all we've done so far is make a specific choice for F. In some sense, it's a very symmetric choice. For every binary vector of the same Hamming weight, it's the same thing, right? And indeed, like it's a not too hard to understand choice in the sense that at least it's a clean function, and then we can do some analysis. Okay. All right. Now, notice that for any fixed x, AF of x, so think of f being like a function, a being an operator, a is a matrix. So one way of thinking about this is a is a matrix, which is a 2 to the n by 2 to the n matrix, operating on f, which is a length 2 to the n vector. So this AF is something which is operating on So which is operating on X. So okay, forget the functional representation. Just think of the matrix representation. So you have A times F. That is precisely equal to F of X plus EI, X plus the unit vector. Why is that? Because A is the adjacency matrix, right? It looks at like X is connected to X prime only if the Hamming distance between X and X prime is exactly 1. So when I multiply A with F, then I'll end up with some F prime where the F primes will have support exactly at the X primes which differ from X in exactly one location, right? So therefore, that's exactly corresponding to F of X plus EI, where EI is a unit vector, like corresponding to which location X is flipped in, right? And this is I can take any value from 1 to n. Okay, so since the F itself is symmetric, that means it depends only on the Hamming weight of X. Therefore, AF is also symmetric. In particular, AF of I, like that is AF operated on any X of Hamming weight I, is I times F of I minus 1 plus n minus I times F of I plus 1, right? Because there are I vectors of Hamming weight I minus 1 which are adjacent to X, and n minus I vectors of Hamming weight n I plus 1 adjacent to X, right? Because you have to flip a bit. Either you're flipping a bit from 1 to 0 or 0 to 1. You had originally I ones in it. So now if you flipped a 1, you get I minus 1 ones. If you flip a 0, you get I plus 1 ones. And the corresponding number of ways you can do that is exactly this. Okay. Also, within this range, Fi over Fi plus 1 is, well, you just take the ratio over here, right? Fi over Fi plus 1. That ratio is this square root of n choose I plus 1 over n choose I, and simplify it's square root of n minus I over I plus 1. Okay. So now with these facts, this fact over here and this fact over here, you can show that for any I within the range R minus m plus 1 and R minus 1, AF of I is this quantity here. How did I get this? Well, AF of I is I times F of I minus 1 plus n minus I F of I plus 1. F of I minus 1 over F of I is n minus I plus 1 over I, right? Just use this recurrence relationship to substitute that here. Similarly, use a recurrence relationship to substitute F of I plus 1 over here. So then you have F of I over here on the right-hand side, right, by the recurrence relationship. Okay, so therefore you have A times F of I is given by this quantity over here. Therefore, F transpose AF is so when you do that, F transpose AF is summation k goes from k going from this value like this thing over here. Now F of I whole square, right? Because F of I whole square, wait, what just happened here? Yeah, so I just took F transpose AF. So when I do F transpose, now there are 2 to the n terms over here. When I do these 2 to the n terms, when I decompose them into things of Hamming weight k being k going from 0 to n, so the only surviving terms are those where the Hamming weight is in the range R minus m to R, right? And so there's going to be a F of I on the left-hand side, there's going to be a F of I on the right-hand side, so you end up with F of I square or F of k square. That F of k square is going to behave like 1 over n choose I, right? Because for I in the relevant range or k in the relevant range, you have something like this. And all the terms corresponding to that specific Hamming weight k are going to behave like n choose k. At some point I became k, I apologize for the change in notation. But basically, you should think of k and I as being the same quantity. Okay, so this n choose k and F of k square cancel out, and you're just left with the summation square root of k times n minus k plus 1 plus blah 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 from r minus n plus 1 to n minus 1. So you have this thing here. Now, just note that within this range, when k goes from r minus n plus 1 to r minus 1, both of these terms over here are indeed larger than square root of r minus m times n minus r, which is in turn larger than r times n minus, wait, r times n minus r minus a lower order term minus m. Okay, just by a Taylor series or something, you can argue that this is larger than m. M, remember, behaves like square root of n, so it's a smaller quantity. Okay. All right, so what have we shown so far? F transpose AF is bigger than 2 times m minus 1 times this quantity over here. And F transpose F is just summation over all I in this and x of the constant having weight, 1 over square root of n choose I whole square. So that's basically, n choose I divided by n choose I, and you're left with m over here, right? So F transpose F is at most m, right? It's at most the distinct values that I can take or k can take. So that's at most m. So therefore, when you take this ratio over here, that's basically like here you have a m minus 1, there you have a m. So it's larger than, just treat the m minus 1 as m, that's upper bound. So it's larger than this 2 times square root of r times n minus r minus little of n. Okay, so we almost have what we want. We have this quantity here being larger than lambda, but we want AF is bigger than lambda f. And from here onwards, I just copied the Tashma notes. And we're already 5 minutes late. We'll pick this up next class, Thursday onwards. So this argument is basically just saying that for the specific types of matrices A that we have, you can argue that given this inequality over here, you can also argue that AF is bigger than lambda f. That plus the Piron-Frobenius theorem will give us what we want. Okay. All right. Well, I'm out. The other reason I'm stopping is I'm getting hoarse as well. 5 minutes overdue, but also my throat is dying. But let me quickly summarize what we've proven so far. So we want to prove what is almost the tightest bound known, and we have to do a fair bit of work for that. The lower bound, the GB bound, was quite straightforward. It basically just, greedy argument. We looked at 2 different proofs. The upper bound, the LP bound, is quite non-trivial. To prove that, we first proved this lemma over here, arguing that the largest eigenvalue for any support restricted f is at least as large as this quantity. So we gave a lower bound. It's basically algebra. There's not much. I mean, there's a very cute ideas in there, but after that it's basic algebra. For the other bound, we'll have to do Fourier analysis, which is to show, okay, if the largest eigenvalue is sufficiently large, then the size of the code is no larger than this b over here. Okay, and that we'll do next class. That'll be Thursday. Remember, by the way, the Thursday class will be in, I don't know, 733 or something like that, right? In a different classroom. So remember that. And then as a consequence of these two, we just did a few calculations and we showed that this gives us basically the first LP bound over there. Okay. All right, that's it. I apologize for running over time. Any questions before we stop? Yeah, this is proof by tiredness. Yeah, so at the end of a whole bunch of mathematics, people get tired. Okay, thank you guys. We'll pick this up on Thursday. And thank you, Ihan and Eric. Thanks for participating.
So I'm still confused about this. You said the support of f is infinite. So can I have a numerical example? For example, f1 is 1, f2 is 2, and you say what do you mean by support of f is infinite?
Okay, so yeah, so let's just say n is yeah, and okay, so and let's say b is
that's what is here. So B is 1, 1, 0, 0, 1, 1, and 1, 0, 1. Okay. So this is specifying that subtiming weight here. So now, what possible f's can I think? So f must be yeah. So now I want.
I suddenly confused myself. Yeah, just a second. Let me just switch off this video.